In exercise 1 to 10, assume that T is a linear transformation. Find the standard matrix of T. So 1, we have T from R2 to R4. TE1 is 3131. TE2 is minus 5200. Where E1 is 10 and E2 01. We know that the standard matrix A is given by TE1, TE2. Since here we have, this is the transformation from R2 to R1. So our standard matrix A is equal TE1, it is given here 3131. TE2, it is given minus 5200. So this is our standard matrix A. Three, we have the transformation from R2 to R2 rotates points about the origin through 3 pi over 2 radians counterclockwise. We know that the standard matrix of rotation, it is given by cosine theta sine theta and minus sine theta cosine theta. So here, since our theta is 3 pi over 2 and it is counterclockwise, that means our theta is positive. So A is given by cosine 3 pi over 2 sine 3 pi over 2 and here minus sine 3 pi over 2 cosine 3 pi over 2. And this one will give us cosine 3 pi over 2, it is 0. Sine 3 pi over 2 minus 1 minus sine 3 pi over 2, it is 1, and cosine 3 pi over 2, it is 0. So this is our standard matrix A. So number 5, the transformation from R2 to R2 is a vertical shear transformation that maps E1 into E1 minus 2E2. So that means E1 will be equal E1 minus 2E2, but leaves the vector E2 unchanged too. So E2 will be equal E2. We know that the identity matrix I2 is equal 1, 0, 0, 1. So after the transformation T, our matrix will be changed as. So E1 will be E1 minus 2E2. So this is 1 minus 2 multiplied by E2. So this is 1 minus 2 multiplied by 0 will be 1. Then here we have 0. So 0 minus 2 multiplied by 1 will be minus 2. Then E2 will be the same. So this is 0, 1. So this is a vertical shear transformation. In 7, we have the transformation from R2 to R2. First rotates point through minus 3 pi over 4 radian clockwise. So we know that if we have our matrix A is 1, 0, 0, 1. So after the transformation, that's mean rotates point through minus 3 pi over 2 radian clockwise. So this will give us cosine minus 3 pi over 4 sine minus 3 pi over 4, then minus sine minus 3 pi over 4 cosine minus 3 pi over 4. This minus, because of the theta is here, it is clockwise, so that's why here we have minus. So then the result will be equal. So this is after rotating this one through minus 3 pi over 4 clockwise. So cosine minus 3 pi over 4 will be minus 1 over root 2. Sine minus 3 pi over 2 will be minus 1 over root 2. Then minus sine minus 3 pi over 2 will be 1 over root 2. And cosine minus 3 pi over 2 will be minus 1 over root 2. So then reflects points through the horizontal x1 axis. So here we have a reflection point through the horizontal x1 axis. If we do reflects about x1 axis, that means x2 will be changed and x1 will remain the same. So after reflection, here we have reflection about x1 axis. This will give us, if we do reflection about x1 axis, the y2 will be changed. So here minus 1 over root 2 will be the same. y2 will be changed, so it will be 1 over root 2. 1 over root 2 will be the same. And y2 here, or x2, will be changed, so this one is minus 1. Sorry, it will be plus, because the reflection about x1, so this will be 1 over root 2. So the first one, rotation minus 3 pi over 2 clockwise, and the second one is reflection about x1 axis. In 8, the transformation from R2 to R2 first reflects points through the horizontal x1 axis. So if we do reflection about x1 axis, x2 will be changed. So if we have our matrix A is equal 1 0 0 1. So after reflecting this one through x1 axis, so here we have reflection about x1 axis, that means x2 will be changed. So 1 will be the same, 0 will be the same, this one will be 0, this one will be minus 1, because we do reflection about x1 axis. Then reflects points through the line x2 will be equal x1. So again we have here reflection x2 is equal x1. So that means we need to interchange between x2 and x1. So this will give us 0 1 minus 1 0. So in 9 we have transformation from R2 to R2. First performs a horizontal shear that transforms E2 into E2 minus 2E1, leaving E1 unchanged. So first we have A is equal 1 0 0 1. So the transformation here, we have first E2 is equal E2 minus 2E1. So E2 will be equal E2 minus 2E1, leaving E1 unchanged. So E1 will be equal E1. So E1 will be the same, this one E1, 1 0. Now for E2 we have 0 minus 2E1. So 0 minus 2 will give us minus 2. Then we have 1 minus 2 multiplied by 0. This will give us 1. So this is the first transformation. Then reflects points through the line x2 is equal minus x1. So another reflection here we have x2 is equal minus x1. So we need to interchange between x2 and x1 and put x2 is equal minus x1. So here this will give us 0, minus 1, then 1, 2. We interchange. So x2 will be equal minus x1. Minus 0 will be 0. So x2 will this one is x1 will be minus x2. So get 0 minus 1. Then for this one we interchange it with x1 and put this one is minus. So it will be minus 1. And so sorry, this one is minus 1. And here we have 2. So this is a reflection. First we have E2 is equal E2 minus 2E1. Then we have another reflection, x2 is equal minus x1. The first one is shear, horizontal shear transformation. The second one is reflection. In number 10, we have T from R2 to R2. First reflects points through the vertical x2 axis. Then rotate points pi over 2 radians. So we have our matrix A is equal 1 0 0, 1. So first we have reflection about x2 axis. So reflection about x2 axis. We know that if we have reflection about x2 axis, x1 will be changed. So that's mean minus 1, 0, 0, 1. Then the second one rotates points pi over 2 radians. So here we have rotation about pi over 2 radians. Now for the rotation pi over 2, we know that the standard matrix for rotation is given by cosine theta, sine theta, then minus sine theta, and cosine theta. Now we want to rotate these two vectors. The first one minus 1, 0, the second one 0, 1. If we use this matrix, so that means we need to first rotate minus 1, 0. So we multiply the matrix pi minus 1, 0 to find what is the transformation of t minus 1, 0. So now this will give us our theta here is pi over 2. So let us write it here from here directly. We'll take the first vector, which is minus 1, 0. So from here our theta is pi over 2. So now cosine pi over 2, we know this one is 0. So this is 0, also this one 0. Sine pi over 2, that's mean it is equal to 1 minus sine pi over 2, this one is minus 1. So our matrix will be 0, 1 minus 1, 0 multiplied by the vector minus 0, 1. This will give us 0 multiplied minus 1 plus minus 1 multiplied by 0, this one 0. Then 1 multiplied minus 1 plus 0, so minus 1. So the first transformation of this matrix will be 0, minus 1. Now for the second transformation, so we have the second vector 0, 1. So now t for 0, 1, this will be 0, 1 minus 1, 0 multiplied by 0, 1. This will give us 0 multiplied by 0 plus minus 1 multiplied by 1. This one is minus 1. 1 multiplied by 0, 0, 0 multiplied by 1, 0. So the second will be minus 1, 0. Or you can do this one by a graph. Making a graph, you have your first one is minus 1, 0. So here minus 1, 0. If you rotate this one by pi over 2, that's mean here we have this one is pi over 2, which is 90 degrees. So the new vector will be here. So if this point is minus 1, 0, this point will be 0, minus 1, and we get the first one. For the second one, we have 0, 1, so our point will be 0, 1 here. If you rotate this one pi over 2, that's mean 90 degrees, so this one will be here. So this is a vector minus 1, 0. So either you use this procedure or you use this one, both of them will be correct. In 11, a linear transformation T from R2 to R2 first reflects point through the x1 axis. So if our matrix A is equal 1, 0, 0, 1, then the reflection will be through the x1 axis, that's mean x2 will be changed. So reflection about x1 axis, that's mean x2 will be changed. So 1, 0, 0, minus 1. Because x2 is this one, 0, 1. 0 will be the same 0, but 1 will be minus 1. So then reflects point through the x2 axis. So now we also reflection about x2 axis. 1, 0, 1, 0 multiplied by 0, 1, 0 multiplied by 1, 0. That means x1 will be changed. So x1 is 1, here we have, it will be minus 1. x1, this will be 0, so this is 0, and x2 will be the same. So the reflex point through the x2 axis show that t can also be described as a linear transformation that rotates point about the origin. So this is the first part. The second part, we have to show that or to be described, that transformation is described as a linear transformation that rotates points about the origin. So we know that if we have this one rotation, this one is cosine theta, sine theta, minus sine theta, cosine theta. Let T be from R2 to R2 be the linear transformation such that TE1 and TE2 are the vectors shown in the figure. Using the figure, sketch the vector T21. So we are given the vector TE1, TE2. We need to sketch the vector T21. We know that the vector 21 can be represented as 2E1 plus 1E2. So now T21 will be equal to TE1 plus 1 TE2. So now 2 TE1, that's mean we need to duplicate, or we need to multiply TE1 by 2. So if this one TE1, we need to sketch TE2 in the same line of TE1. Let's say this one is 2. So this is 2E1. Similarly, here we have 2 TE1 plus 1 TE2. So we need to add 2 TE1 plus TE2. So we will take this one here and we put it there parallel. So this one approximately is same as this is 2 TE1 plus TE1. So the vector will be here. So this is the new vector is 2 TE1 plus TE2, which is the transformation of 2 and 1. Because we make the parallelogram, which is here 2 TE1 plus TE2, we get the result this one. In exercise 15 and 16, fill in the missing entries of the matrix, assuming that the equation holds for all values of the variables. So here we have a matrix 3 by 3 multiplied by a vector x1, x2, x3. The result or the transformation will be in this form. So A should be equal just the coefficient of these entries. So for x1, the coefficient of x1 here 3, this one 4, 1. So the first column will be 3, 4, 1. Now the coefficient of x2 from here it is 0. Then the second one 0. The third one is minus 1. Then the coefficient of x3 from here minus 2, 0, 1. So minus 2, 0, 1. So this is our matrix A, because if we multiply this one by x1, x2, x3, we get this result. So this is our matrix A. In exercises 17 to 20, show that T is a linear transformation by finding a matrix that implements the mapping. Note that x1, x2 are not vectors, but are entries in vectors. So we need to do 17 and 19. So first for 17, we have tx1, x2, x3, x4 is equal 0, x1 plus x2, x2 plus x3, x3 plus x4. So that's mean t x1, x2, x3, x4 is equal, we know it is a matrix multiplied by A multiplied by the vector x1, x2, x3, x4. We need to find the matrix A So we need to find the matrix A such that this one is equal 0, x1 plus x2, x2 plus x3, and here we have x3 plus x4. So from here it is clear that A is equal the coefficient of x1 0, 1, 0, 0, then the coefficient of x2 0, 1, 1, 0, the coefficient of x3 0, 0, 1, 1, and the coefficient of x4 which is 0, 0, 0, 1. So this is our matrix A that we implies to the vector x1, x2, x3, x4, and we get this mapping. For 19, similarly, we have tx1, x2, x3 is equal x1 minus 5x2 plus 4x3, x2 minus 6x3. So that's mean t x1, x2, x3 is equal the matrix A multiplied by the vector x1, x2, x3. So that's mean here we have x1 minus 5x2 plus x plus 4x3, sorry. Then we have x2 minus 6x3. So that's mean the transformation here we have our matrix A. It is multiplied by the vector x1, x2, x3. So the coefficient of x1 is 1. The coefficient of x1 here it is 0. Then the coefficient of x2 minus 5. Coefficient of x2 1. Coefficient of x3 4. Here minus 6. So from here our A will be equal 1, 0, minus 5, 1, 4 minus 6. In 21, let T be from R2 to R2 be a linear transformation such that Tx1, x2 is equal x1 plus x2 for x1 plus 5x2. Find x such that Tx is equal 3, 8. We know that Tx is equal Ax, it is equal to whatever B here. So we are given B, we are given from here we can get A. Now we are looking for x such that Ax is equal B. So from here what we given here, it is given Tx1, x2, it is equal to x1 plus x2, 4x1 plus 5x2. So that's mean our matrix is 1, 4, 1, 5. Our x is x1, x2. So now we have our matrix A and we have B, we are looking for x. So we need to do row operation for AP. That's mean our A is 1, 4, 1, 5. Our B here it is 3, 8. So we will do row operation. Row 2 is equal minus 4 row 1 plus row 2. This will give us 1, 0, then here 1, then 1, 3, minus 4. So from here, x2 is equal, or x2 is equal minus 4, x1 is equal 3 minus x2, which is equal 3 minus minus 4 is equal 7. So our x is equal 7 minus 4. In exercises 23 and 24, mark each statement true or false, justify each answer. So 23a, a linear transformation T from Rn to Rm is completely determined by its effect on the columns of the n by n identity matrix. This one is true because we say that Tx, it is equal a of x, and our a is Te1 until Ten. So the first statement is true. So this is x here, whatever x here. So a is true. Now b, if t from R2 to R2 rotates vectors about the origin, so that's mean x1 will be changed and x2 will be also changed through an angle theta. Then T is a linear transformation. We say that the rotation is a linear transformation, so this one is true. This is just a reflection about x1 and then reflection about x2 axis. And we say that the reflection is always linear transformation. So C, when two linear transformations are performed one after another, the combined effect may not always be a linear transformation. So if we do a linear transformation, then we do another linear transformation, it said here the combined effect, so the final result will be not always be a linear transformation. This one is false. If we perform a linear transformation, then we do another linear transformation, we should get also the result be a linear, or the combined effect will be a linear transformation. D, a mapping T from Rn to Rm is onto Rm if every vector x in Rn maps onto some vector in Rm. We said that the vector Rn to Rm, if every vector x in Rn maps onto some vector in Rm. This is false. This is the definition of a one-to-one. We said that the Rm, the vector or the mapping is onto if every vector x in Rm has at least one vector x in Rm. So this one is false. For E, if A is 3 by 2 matrix, then the transformation Ax cannot be 1-to-1. This one is 3 by 2 matrix. So that's mean we have 3 rows, 2 columns. Then the transformation cannot be 1-to-1. This one is false. Because we said for a 1-to-1 transformation, we can have columns which are linearly independent, or we can have at least, if we have a 3 by 2, this is can be shown in example 5. Because in example 5, we see that our matrix is 3 by 2, and if we have the columns are linearly independent, that's mean the matrix is 1, or the transformation is 1-to-1. In 24a, Not every linear transformation from Rn to Rm is a matrix transformation. This one we said it is false because it is from theorem 10. It said if the transformation from Rn to Rm, if it is linear, then it should be a matrix transformation. B. The columns of the standard matrix for a linear transformation from Rn to Rm are the images of the columns of the n by n identity matrix. This one true from theorem 10 also, because we said it is TE1, TE2, the matrix, this one. Then for C, the standard matrix of a linear transformation from R2 to R2 that reflects points through the horizontal axis, the vertical axis, or the origin has the form A0, 0D, where A and D are plus or minus 1. This one is... So in C we see that the reflection through the horizontal axis, that means we need to reflect through the x1 axis, so x2 will be changed, so we will get 1, 0, 0, minus 1. Reflection through the vertical axis, so that means reflection through the x2 axis, that means x1 will change, will be minus 1, 0, 0, 1. Then reflection through the origin, x1 and x2 will be changed, both of them. This will be minus 1, this one will be minus 1. So this statement is true. So now for D, a mapping T from Rn to Rm is 1 to 1 if each vector in Rm maps onto a unique vector in Rm. We said this one is false because we need each P in Rm is the image of at most 1x in Rn. So here we said each B in Rm is the image of at most 1x in Rn. Now for E, if A is a 3 by 2 matrix, then the transformation XAX cannot map R2 onto R3. This one is true because for mapping from R2 onto R3 we need 3 pivot columns and we have only 2 columns. So this one we said true. We need 3 pivot and we have only 2 columns. Determine if the specified linear transformation is 1 to 1 and onto. Justify each answer. We know that the transformation it is onto if we have a pivot in every row. And we know also that the transformation, that means the columns here span Rm. And we said that the transformation is 1 to 1 if we have a unique solution or if the columns are linearly independent. So now in 25 we need to see the transformation exercise 17. We know that A is equal, this is from 25, 0, 1, 0, 0, then here we have 0, 1, 1, 0, also 0, 0, 1, 1, 0, 0, 0, 1. So this is, we get this one from exercise 17. So to check that if our transformation is onto, we have to see if we have a pivot in every row. So for the first row there is no pivot. Here we have a pivot in the first one. Here we have a pivot. Here we have a pivot. So this one does not have a pivot in every row. It is not 1 on 2. So it is not on 2 because we have no pivot in every row. Now if we see this one, if it is 1 to 1, we said that the function should have a unique solution, but since for this column we have seen here we have a free variable, so that's mean either we have a free variable, that's mean our function, or sorry, our transformation maybe is has a free variable, so that's mean maybe it not be 1 to 1, or there is no solution. So this one is not 1 to 1. Because here, because of this form of the columns, because either we have a free variable or either the system has no solution, that's mean it is not 1 to 1. In 27, our matrix is 1 0 minus 5 1 4 minus 6. So this one has a pivot in every row, so that's mean the column span R2 maps R3 onto R2. So this one is onto because we have a pivot in every row. That's mean T maps R3 onto R2. This one is not 1 to 1 because here we have x1 has a pivot, x2 has a pivot, but for x3 it's here we may have a free variable because we cannot have a pivot in every columns. So here we can say it is not 1 to 1 because we have a free variable, because there exists a free variable which is x3. In 29 and 30, we need to describe the possible echelon forms of the standard matrix for a linear transformation T. Use the notation of example 1 in section 1.2. So for T from R3 to R4 is 1 to 1. So A should be, since we have from R3 to R4, that's mean our A should be 4 by 3. And if it is 1 to 1, that's mean we have a pivot in every row. So A has a unique solution. So if we write this one, the possible form, for example, if we have pivot in the first row, so this one will be 0, 0, 0. Then here we have a star. We have pivot also in the second row, 0, 0. Then we have here pivot, and the last entry here could be 0. So this one is a 1 to 1 because it is consistent and it has a pivot in every row. So now for 30, we have T from R4 to R3 and we need it to be onto. So our A will be 3 by 4, and since we said it is onto, so that's mean we need to also a pivot in every row and column span R n. So we may have this form. Here we have a pivot, then 0, 0. We have a star, another pivot, 0. We have a star, star. We have a pivot. For the last column, we may have any value. So this one is onto, since we have a pivot in every row. Or we may have another form, for example, this one is here. then we have 0, 0, and we may have here a star, then we have 0, 0, may have here a star, here a pivot, this one is 0, then we may have here a star, and here we have another pivot. Or we may have another form, which is this one is 0, 0, 0, then we have a pivot here, then 0, 0, then we may have here a pivot, another pivot, 0, 0, then the last one also we have a pivot. So you either choose any one of these will be correct because we have a pivot in every row. In 31, let T be from Rn to Rm be a linear transformation with A its standard matrix. Complete the following statement to make it true. T is 1 to 1 if and only if has dash pivot columns. Explain why the statement is true. So our matrix here, it is A is m by n. We said this one is 1 to 1 if and only if A has n pivot. Why we say that n it has n pivot? We know that the transformation T is 1 to 1 if and only if the columns of A are linearly independent. So the columns of A are linearly independent. That's mean the columns of A are linearly independent. That's mean if and only if A has a pivot and columns. This happens if and only if A should has an pivot columns. So we know that T is a 1 to 1 if the columns are linearly independent, and the columns are linearly independent if and only if A has an pivot columns. In 32, let T be from Rn to Rm be a linear transformation with A its a standard matrix. So we know from here that A is m by n. So complete the following statement to make it true. T maps Rn into Rm if and only if A has dash pivot columns. So we know that T maps Rn onto Rm if and only if A has m pivot columns. That's mean pivot in every columns. Because if the columns of A are span Rm, then by theorem 12, this happens if and only if A has a pivot position in each row. And since A has m rows, this happens if and only if has m pivot columns. So we can say here T maps Rn onto Rm if and only if the columns of A span Rm. This is by theorem 12. And this happens, so this happens if and only if A has a pivot position in every row. So here in every row. This is by theorem 4. Theorem 4, section 1.4. So now, since A has m rows, this happens if and only if A has m pivot columns. So this will be having if and only if A has m pivot columns. In 33, verify the uniqueness of A in theorem 10. So let T be from Rn to Rm be a linear transformation such that Tx is equal Bx for some m by n matrix B. Show that if A is the standard matrix for T, then A should be equal B. We know that by definition, the standard matrix A is given by Te1 until Ten. So now Tej for any Ej column here, it will be equal Pej according to this one, Tx is equal Bx. This one will give us the Bj column, where the jth columns of B. So this is the jth column of B. So from here, A will be equal B1 until Bn, which is equal B. So if we have a transformation, linear transformation from Rn to Rm where Tx is equal Bx, this Bx should be a unique. In 34, why is the question is the linear transformation T onto an existent question? Because here we said that the transformation T maps Rn onto Rm if and only if for each y in Rm there exists an x in Rn such that y is equal Tx. So we can write here the transformation T maps Rn onto Rm if and only if for each y in Rm there exists an x in Rn such that y is equal Tx. So that's why we said that T is the linear transformation T onto. This is an existent question because we are looking that for every y in Rm there exists should be an x in Rn such that y is equal Tx. So for every x for every y there exists x such that y is equal Tx. In 35, if a linear transformation from Rn to Rm maps Rn onto Rm, can you give a relation between m and n? And if T is 1 to 1, what can you say about m and n? We know that if the columns or if the mapping map Rn onto Rm, that means we need to have m pivot rows. We need to have a pivot in every row. But what is the relation between m and n؟ على أساس أنا أحصل على عدد m من البيفوت لازم إنه يكون عدد الكولومز أكثر من عدد الروس أو يساويها. يعني نحن قلنا إنه اللي بيكون اللي هو onto Rm المابينج from Rn onto Rm إذا كان عندي pivot in each row. الحين إيش العلاقة between الm والn؟ أنا إذا أريد pivot in each row إذا لازم يكون عندي نفس عدد الكولوم أو زيادة على أساس أن أحصل pivot in each row. So this is 4 and 2. If T is 1 to 1, what can you say about M and N? إذا كانت 1 to 1 قلنا لازم يكون system consistent with unique solution. فالحين على أساس يكون consistent with unique solution إذا كل columns لازم يكون عبارة عن pivot. إذا معناته لازم يكون عدد الروز أكبر من أو يساوي عدد الcolumns. So let us write it here. So إذا كانت 1 to 1 So if T, let's say if T mapping Rn into Rm, that means it is maps Rn into Rm, then standard matrix A should has a pivot in each row. طيب على أساس we have a pivot in each row لازم يكون عندي أصلا عدد الكولومز وعدد الرو يا متساويات يا إنه الكولوم زيادة. So A must have at least as many columns as row. يعني بالمختصر إنه الM less than or equal to 1. إذا أنا على أساس أحصل المابينج يكون on 2RM لازم we have a pivot in each row. طيب أنا هل ممكن لكل ماتريكس أحصل pivot in each row؟ أيوة، بشرط إنه يكون عدد الكولومز يساوي عدد الرو أو عدد الكولومز أكثر عن عدد الروز. الحين لما نيجي نتكلم عن ال 1 to 1 so when T is 1 to 1 so A must have a pivot in each column أساس يكون عندي unique solution. كل المتغيرات لازم تكون basics. So that mean إنه الM لازم تكون greater than or equal to 1. يعني لازم يكون عندي enough row على أساس إن أنا أحصل pivot in each column. So إذا كانت on 2 لازم الM less than or equal to 1. إذا كانت 1 to 1 لازم الM greater than or equal N. In 36, let S be from RB to Rn and T from Rn to Rm. Be a linear transformation, so let us write here S is from RB to Rn and T is from Rn to Rm. Both of them are linear transformation. So now show that the mapping X T as X is a linear transformation from RB to Rm. Hence compute T as Cu plus dV for UV in RB and scalar CD. Justify each step for the computation and explain why this computation gives the desired conclusion. So now we need to show that T as Cu plus dV is a linear. That means it is equal to Ct as Cu plus dt as V. So now let us take two vectors. Let U and V be in RB, sorry. And let C and D scalar be scalars. Then we have now T as Cu plus dV. This is equal to T CSU plus DSV, because we said that S is linear. So this is because S is linear. So for this one we can, because S is linear, we can rewrite this one, the inner one, as CSU plus DSV. So this will give us, we can take C out, so C T SU plus, also we can take D out, D T S V. Why we do this? Because we see also T is linear. So now, because TSCU plus dV is equal CTSU plus dTSV, this show that إنه XAX or sorry TSX is a linear transformation. لأنه نحن قلنا من واحدة من ال properties of linear transformation إذا قدرنا we show that إنه TCU plus dV is equal CTU plus C plus dTV. فهنا بما أنه عندي two combine of two linear transformation فهو صار mixed. إذا بعد ما سوينا لها rewrite because ال S is linear, T is linear, we get this form which show that إنه this one is a linear transformation.